Hello, everyone, and thank you for standing by. Welcome to this ASM webinar on the future of transport, grasping new opportunities in heat treating. I'm Vicki Burt, editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series, designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. This series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsors of today's webinar are Linde and Nitrex. Linde is a leading global industrial gases and engineering company with 2021 sales of $31 billion. They live their mission of making our world more productive every day by providing high-quality solutions, technologies, and services, which are making their customers more successful and helping to sustain and protect our planet. Linde also delivers state-of-the-art gas processing solutions to support customer expansion, efficiency improvements, and emissions reductions. Nitrex is the only fully integrated global player in the surface treatment industry. With a presence in more than 20 countries, their portfolio of innovative solutions and unrivaled expertise are helping customers daily to achieve greater tolerances, meet the highest standards, and become more profitable along the way. With over 35 years of experience under their belt, Nitrex is the preferred choice of blue-chip customers around the globe for turnkey heat treat systems, reliable technologies with over 4,000 proven formulas, proprietary high-end instrumentation, fail-safe digital controls, and surface treatment services. We're proud to have Linde and Nitrex on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the questions window. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is the flagship publication from ASM International. It provides information about leading-edge developments and trends in engineering materials, and the methods used to select, process, fabricate, test, and characterize them. With that, I'd like to introduce the instructors of today's webinar, Carl Schultz and Jack Kaluki. Carl Schultz is the Global Commercialization Manager of Metal Fab and Heat Treatment at Linde. He has over 10 years of production management in copper and brass alloy production. He also has 6 years of military service with the U.S. Army, serving as a UH-60 Black Hawk helicopter mechanic and crew member. Carl has a Bachelor of Science degree in Industrial Engineering and is a Lean Six Sigma Black Belt. Jack Kaluki is a technological advisor at Nitrex, supporting industrial customers in North America and parts of Europe. He has over 30 years of experience with nitriding and nitrocarburizing process material and application development in demanding industries such as aerospace, automotive, defense, gears, and tooling, with roles in customer service, R&D, heat treating services, and technical sales. And now it is a pleasure for me to introduce Carl and Jack.
Hello. So now I'm just going to get started here real quick. Shut off our cameras. What we decided to do is shut off our cameras for the presentation, and we'd be turning them back on for the Q&A session. I just wanted to start by kind of giving an overview of Linde itself. As mentioned, 2021 sales is $31 billion US dollars, operating in over 100 countries globally. Our business segments include the Americas, EMA, which is Europe, Middle East, and Africa, APAC, Linde Engineering, and then Global Others. The end markets include chemicals and energy, healthcare, manufacturing, metals and mining, food and beverage, electronics, and others. Our distribution modes are packaged gases, merchant, on-site, and then others. Some of the other kind of breakdowns of our gases are atmospheric gases, so nitrogen, oxygen, argon, and then rare gases like krypton, neon, xenon. Process gases include acetylene, helium, propane, carbon dioxide, carbon monoxide, hydrogen. Medical gases, medical oxygen, nitric oxide, nitrous oxide, and then specialty gases.
Thank you very much, Carl. Good morning, everyone. Very fast introduction for Nitrex. Nitrex has really started as a company specialized in automation technology and mostly creating control systems. Today, the company has evolved. It has three main divisions. The first one is called HTS, but in general, it is a commercial heat treating service or services with plants located everywhere worldwide, including the US, Mexico, Brazil, China, parts of Europe. Then you have the main core of the company, which is called today NTS, specialized in heat treating technology and equipment. This part of the company builds control systems, builds furnaces, which includes nitrocarburizing furnaces, nitriding furnaces, and vacuum furnaces, with an emphasis on providing recipes and technological help and support to our customers. Finally, there is the instrumentation branch of the company called UPC Marathon today, which specializes in OEM supplies, which includes flow meters, oxygen probes for carburizing, for instance, gas analyzers for nitriding and other applications, gas mixers, gas generation, as well as automation software for applications such as lights out plants. Next. Thank you. This is the general agenda of the meeting this morning. Well, we are going right now over the introduction, and then we'll talk about the Nitrex perspective on industrial gases as an end user and equipment supplier. Of course, we always have to deal with many issues because gas and technical gas is really at the core of our business. Then we'll talk about core competence, process controls, gas analyzers, and challenging applications. The section that Linde will talk about is the other processes beyond heat treatment, and this applies in majority to electric vehicles and the change in the industry. Finally, I will talk about particle emission reduction case. This is something brand new, has surged in the past few years, and I'll expand on this later. It is one of the great case studies that will illustrate how the industry is changing today. And finally, Linde will talk about the need for pointed gas process control and high quality gases in heat treatment and other industries. Next. Thank you very much. So you probably, being in the business of heat treatment or transportation, you have seen that in the recent years, on the one hand, internal combustion engines have had a rougher time and have been eliminated or will be eliminated in some part of the world, including Europe, by probably the end of this, probably by 2030. And we always think that this will also eliminate some of the processes. It definitely will, but also there are many new opportunities that are rising with the transportation industry evolution. So there are two key trends, which are electrification and connectivity. Connectivity has more to do with smart cars and self-driving systems and so on. But and they all apply, of course, to different forms of transportation. But electrification is one of the main factors that we are seeing as a heat treater and gas supplier. What is driving those trends is mainly policy changes, which have to do, of course, with the reduction of pollution, reduction on impact on our environment, and mostly driven by meetings such as COP, which right now has taken place, and different new legislations that are covering Europe, but as well North America as well. Next. Okay, I'll describe very shortly, succinctly, our perspective on industrial gases as an end user and equipment supplier. Next. Thank you. So it is a bit misleading. We talk about heat treating in general. Most of the processes are not really just heat treating processes. High value added processes are usually more described as such as thermochemical processes. This applies to nitriding and nitrocarburizing. It also applies to carburizing and low pressure carburizing. Finally, in the vacuum heat treatment, yes, you do have classical heat treatment, but also different other coatings that are being applied. So it's a really vast world of that has to do with, yes, of course, heat treatment, but also thermochemical treatments. Next. Thank you. So these are the locations, the main locations of our plants. Sorry, maybe it's not very accurate, but we have plants in China, in Italy, in Poland, of course, in Montreal, Canada, which is our worldwide headquarters, and several locations in the US, in Mexico, as well as in Brazil. Overall, the gases that we are using are ammonia, acetylene for LPC, argon for vacuum, hydrogen for some of the vacuum processes, carbon dioxide, carbon monoxide, nitrous oxide, which is mainly used as a post-oxidation gas, propane, which is used sometimes as a gas in nitrocarburizing, natural gas, as well as helium, which may be used in processes such as LPC, but also for leak detection. To give you the numbers, which are astounding, overall worldwide, we are using over 3 million kilograms of nitrogen, 500,000 kilograms of ammonia, and over 60,000 kilograms of carbon dioxide, which is mainly used again for nitrocarburizing. Next, please. What we have seen in the most recent evolution in the transportation industry has a huge impact on demand. One of the factors that drives this demand is a new changes in purchasing patterns and replacement of all the combustion vehicles by electric vehicles or hybrid vehicles, which have basically the same needs. Nitrocarburizing is used a lot for components such as brake components, chassis components, because it's a process specialized in sliding wear and anti-corrosion, among others. So the volumes have been increasing, which calls for completely different solutions. Most of the nitrocarburizing processes are relatively short, meaning that they last between less than 3 hours and perhaps over 6 hours. This means that big pit furnaces are not very practical because your heating time and cooling time requires a long time because of the volume and the weight, and the process itself is relatively short. Therefore, we are evolving towards equipment which is either continuous or semi-continuous to be able to provide solutions for this kind of demand. Next, please. Thank you very much. The other aspect of our business is also heat treatment of aircraft engine parts. So it is an evolution. We are thinking, of course, of evolving vehicles such as electric cars and so on, but it is very surprising that new engines, those turbofans that we are seeing right now, with the improvements in the blades and the types of compression they can achieve, have an extremely good mileage. If we go to the next slide, we'll see some of the components. Thank you very much. So those are called the single crystal blades and vanes, and they are used in the hot part of the engine. The cold part that we see as passengers on an airplane is usually a composite with the leading edge made with the materials such as titanium. But inside the engine, you have this type of vanes and blades, and those allow higher compression ratios, very hard working environments, and the processes which are used are usually vaporized aluminite coatings. This is used also in military airplanes. But as a passenger taking an airplane, you have a carbon signature. Newer engines have an extremely low carbon signature. Of course, it's the quantity of flights that counts, but as a passenger, you get roughly 90 miles per gallon. So this is astounding when you think of the sheer quantity of fuel being used in aviation. Those engines allow lower and lower usage of fuel and lesser pollution. Next, please. The main gases used in vacuum applications are nitrogen, argon, and hydrogen. Next, please. Thank you very much. So we are coming to LPC. LPC is a newer, leaner, and probably less polluting way of carburizing components. Electric vehicles have relatively simpler or different gearboxes from classical vehicles, whether we think of a manual gearbox or automatic or semi-automatic. In this case, you have many solutions. When you look at different manufacturers, everyone has his own. But LPC technology really provides a better environment to operate. It's more precise, it is less polluting, and even though the equipment itself may be very expensive at the beginning, the operating cost and pollution generated by the equipment are worth it. I believe that Carl can elaborate a bit more on this process.
Yeah, thanks, Jack. So low pressure carburizing compared to conventional carburizing allows operators to increase their temperatures and shorten the total process times, kind of similar to what Jack was mentioning about nitrocarburizing as well. In combination with high pressure gas quenching, the solution minimizes distortions compared to normal oil quenching. It ensures consistent cooling results with respect to grain structure and hardness. In low pressure carburizing, the optimal selection of gas purity is important also for achieving that outcome. The use of acetylene as a carburizing medium has specific advantages as well. With acetylene, the density of the loads is increased, as well as the length diameter ratio of blind holes. So you can actually get carburizing a little bit further up into blind holes, such as ring gears and things of that nature for their mounting hardware. To ensure and also it ensures to ensure the right flow conditions and support intermittent flows, both low and high pressure, is especially critical when several treatment chambers are present, kind of similar to the image here. And then to the right, it kind of gives a quick description of the process itself and the gases that we use. So nitrogen to purge the furnace, acetylene for the carburizing, and then helium for the quenching. Next, I wanted to kind of talk about an additional step with heat treatment was sub-zero. Currently, with trends towards more vacuum heat treatment and increased demand in sub-zero process in order to transform retained austenite to martensite. And in the image here, it kind of shows an example of one of our sub-zero treatment coolers as well. Another reason to bring it up, as well as the possibility for more shrink fit connections between increasing demand within the electric vehicle market. As an isolated cryogenic step, special freezers can easily be integrated into manufacturers' existing heat treatment processes, typically working at temperatures ranging from -60 C to -180. These treatments take between 4 and 72 hours, depending on the goal of the process. The transformation of retained austenite to martensite can be achieved at a range between -60 C and 120 C, and a dwell time of about 1 to 4 hours, depending on the cross-section of the materials. Applying cooler temperatures between 120 and 180 with longer dwell times will also support precipitation of fine carbines as well, with improved wear and resistance to metal parts.
Thank you very much, Carl. This section really talks about our core competence. We can go to the next slide, please. Thank you. So I mentioned at the beginning that Nitrex does specialize and did specialize at the beginning in research, and the company still invests and reinvests a portion of its revenue in research and development. Why? Because precisely we have new applications and new challenges that are coming from all kinds of industries. This includes new requirements in the automotive sector, as well as aerospace. We have about 150 engineers in different specialties who are either working at Nitrex or contracted or working together with us in different universities on new processes and new solutions. Next, please. Thank you. So among the Nitrex technologies, the first one that came up really was potential controlled nitriding, and it was formulated at the very beginning of the company as a new automated and controlled system that has a closed loop control that analyzes gases, quantifies the reaction occurring inside the furnace, and allows for the precise nitriding and renitriding with the same results from one process to the next, regardless of the number of components inside the furnace or the developed area. Coming second after this was a potential controlled nitrocarburizing. When we started first working on nitriding in 40 years ago, almost, 35 really, there wasn't much demand for nitrocarburizing. It was a process with very wide specifications. However, as companies started using lower and lower quality materials, more carbon steels, the demand for higher quality nitrocarburizing and better controlled processes arose. So we have developed this technology really very strongly for the last 20 years. Together with nitrocarburizing, you see in process post-oxidation or oxidation. The idea here is to basically transform the top of the white layer into magnetite and provide enhanced corrosion resistance. In parallel, we have developed Nitreg-S or Nano-S, two technologies specialized for stainless steel applications. Today, it is a very significant part of our market. Those two technologies apply to very many different materials, ranging from austenitic to martensitic materials, as well as duplex materials and precipitation hard materials. Next, please. Thank you. So here, basically, out of this research, which is really our core competence, have come two main specifications, which are today industry standards. One is 275910, which is automated gas nitriding controlled by nitriding potential, which is, let's say, one step after the 27596, which was basically describing control by dissociation. And then you have 275912, which talks about gas nitrocarburizing, automatically controlled by potentials. It's not a typo. In this case, we have two potentials. One is nitriding potential, and the second one is the carburizing potential. So you have a Kn and a Kc that are being controlled together in order to achieve the right white layer composition in terms of gamma prime and epsilon. Next, please. Thank you. So this is the UPC marathon section derived from this research. We have our division, which is supplying to many of our customers, providing upgrades and so on. It specializes in carburizing controls, in endo generators, in automation, process automation, flow control, as well as oxygen probes and full solutions for replacement of all their equipment. And it is part of Nitrex, however, a different division, since it provides solutions for equipment that is not necessarily built by Nitrex. Next, please. To summarize the materials that we are covering as in terms of nitriding, nitrocarburizing, is carbon steels, mostly nitrocarburizing, low alloy steels, here 4140, 4340, very common, which we also process in nitrocarburizing if we have an annealed form in our plants. Tool steels, most common are H11, H13. H13 can also be nitrocarburized for some of the applications. High-speed steels, which is M50, for instance, in this case, there are not many applications. One of them in transportation is bearing races built by certain companies, which are nitrided to a relatively great case depth and treated by Nitrex and using our recipes. You have nitralloys comprising nitralloy 135M and N, and then a whole range of stainless steels. Next, please. Thank you. This is your turn.
All right, this brings us to other processes beyond heat treatment. Starting with looking into the future of transport, there are other industries and processes that play an important role in our topic. One is additive manufacturing. Additive manufacturing is also known as 3D printing or rapid prototyping, the process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing. The use of additive manufacturing with powder metals is a fast-growing industry sector. Has become a suitable process to produce complex metal parts and not only used for more than prototypes. As a matter of fact, in 2021, 28% of all additive manufacturing systems were sold into the transportation industry as well. One of the parts that Linde has been working close with some manufacturers on is metal powder, and it plays an important role in additive manufacturing process. The quality of the metal powder used will have actually major influences on the properties, but it can also influence build-to-build consistencies. the repeatability of the additive manufacturing machines, the production of defect-free components, the manufacturing of defect on the surface as well. So if you see here in the image, you have water atomized powder as well as gas atomized powder, and kind of what they're best used for. Gas atomized powder is easier to flow, low oxygen content, whereas kind of the water atomized powder is non-spherical, bad flowability. It tends to clog up easier, as well as grab a hold of chemical contaminants as well. Powders for additive manufacturing usually produce using gas atomization process, whereas molten metals, steam is atomized thanks to high pressure neutral gas jets into small metal droplets, thus forming metal powder particles that you see in the right image there after rapid solidification. Gas atomize is a physical method as opposed to a chemical or a mechanical means to obtain those medical powders. But powders produced by gas atomization have spherical types, again, like you see in the image to the right, which is very beneficial for flowability, again, repeating kind of what I already mentioned. And this is a kind of a crude description of kind of how we assist with gas atomization and where it actually takes place. So like I had mentioned, it has molten metal that's actually poured down through a spout, and then at that spout, the either nitrogen or argon gas are pressurized at that nozzle in order to create those powders. And then it's collected and cooled inside that chamber and collected. Next is Linde's value chain for metal powders. And as you can see across the slide, it says optimized powder production, and then there's kind of how that is done below it: secure powder handling, excellent 3D printing, and enhanced post-processing. In optimized powder production, the particle atomization process, like I described in the previous statement or the previous slide, the powder shaping, again, for having nice spherical powder as opposed to non-spherical and binding up, and packaging, the aging process, and atmosphere sealing. So one of the problems can actually have moisture or contamination inside the powder itself, as well as the powder itself can be somewhat dangerous depending on how fine it is. You don't want to inhale or breathe any of those things. So Linde actually has some products, powder cabinets, that will actually allow for a controlled atmosphere to preserve those powders as they're being transported or stored on site. Then it also gets into how each one of them is used for the different types of 3D printing, which I'm going to go into a little bit further here in a few more slides, and then the post-processing aspect of that. So the heat treatment of the created objects, such as hot isostatic pressing, thermal spraying, and then surface finishing as well. So if you see here, some of the processes that Linde actually assists with is binder jetting, laser powder bed fusion, laser directed energy deposition, and then arc directed energy deposition. As demand for the additive manufacture process has been steadily increasing, so have the many enabling technologies, increasing laser metal fusion, laser metal deposition, selective laser sintering, wire arc additive manufacturing, thermal spraying, electron beam melting. Products manufactured with these processes and technologies are typically forged, heat treated, or sintered to achieve the quality, finish, and mechanical properties desired. Process gases play a vital role in every step of the AM fabrication chain. Laser powder bed fusion is a process which a high power laser beam is connected to a robot or a gantry system to form a melt pool in a metallic substrate into which powder or wire, metal wire is fed into. We supply customers with gaseous or liquid helium, argon, nitrogen systems to assist with the laser metal deposition process. It's kind of similar to welding in that you kind of still need a shield gas or a gas to protect the powder as it's being formed. In this process, the powder is contained in a carrier gas and directed to the substrate through a nozzle, which is concentric with the laser beam. Alternately, a wire can be fed from the side as well. The powder or wire is melted to form a deposit that is bonded to the substrate and grown layer by layer. An additional gas jet concentric with the laser beam provides additional shielding or process gas protection. The method is suitable for large components where a higher deposition rate is required. Laser powder bed fusion is used for a wide range of applications, including cladding and repairing, carried out for examples as molds to resurface applications for high value parts such as aero engines, components, and military equipment. Laser directed energy deposition, or DED, alternately known as a near net shape, is a process which uses a high power laser beam connected to a robotic or gantry system to form that same pool system. In DED, the powder is contained in carrier gas and directed to a substrate through the nozzle and is concentric with the laser beam. DED is used for a wide range of applications, similar to the laser direct powder bed as well. Gas metal arc welding and plasma welding techniques are used to melt metal filler to form a 3D component layer by layer. Gases are applied to protect the hot substrate, same as as above, against the ambient atmosphere and to assist with metallurgical properties of the component. We offer a wide variety of specialty gases solutions to protect the fine-tuned component materials. As in MIG or mag welding, metal wire is added to the electrode, melts in the arc, and is droplet form layers on the substrate. Process with the lower heat input, such as controlled short circuit metal transfer, are preferred given the heat sensitivity of most materials in the additive manufacturing. So what will happen is it could actually cause warping if it gets too hot, and actually makes it more difficult to build layer upon layer. The shield gases protect the layers against the ambient air. Within the plasma process, the additive manufacturing is like the laser metal deposition in the powder is guided towards the substrate in gas stream and fused by plasma heat. Additionally, the process cooling is generated component required during this welding process, such as CO2, to keep everything from warping and allowing for an even buildup of material. That brings us to hot isostatic pressing. And this is a process which temperatures are raised up to as high as 2,000 degrees Celsius and pressures up to 2,000 bar. And the reason for this is to actually eliminate internal porosity or voids that take place either from a casting process or an additive manufacturing process. Because the metal powder is somewhat porous as it's being either laser welded or whatever style additive manufacturing that is taking place, what the HIP process will actually do is allow for the porosity to be reduced, and it actually shrinks the material itself and increases wear characteristics, as well as it removes any residual stresses that may be in the metal, similar to in an annealing process. With HIP, Depending on the size of the pressure vessel, there can be tremendous amounts of argon that are used, or nitrogen. And Linde has actually developed some processes to actually reuse that argon after it's been used. And this is a kind of an example of which. And then looking at all of these processes and the prediction of sales moving into the future of electric cars, looking to approach somewhere between 50 million and 60 million cars by 2040, and that's internationally. We also touch on the new booming industry of battery cells. Figures on this slide show an impressive growth expectations. And this was actually taken from the March. And a few weeks ago, looking back, they were actually looking at 343 individual lithium ion battery gigafactories in the pipeline to be made, with a total capacity of roughly 7,575 gigawatt hours. So it's an increasingly booming industry. Although the production of batteries does not include classical heat treatment processes, we also do some aspects that could have influence on the heat treating industry as well. There are different types of materials that may require heat treatment. There are processes like lithium roasting that could benefit from classical heat treatment know-how. We see key players from the heat treatment industry that are active in the lithium ion battery industry, particularly for anodes and cathodes on the lithium batteries. There's some efficiency that can be gained through a heat treatment process. Jack?
Thank you very much. I will try to go faster. I think we're getting near the end of our time slot. So we'll go very fast over this interesting reduction of emissions case. Probably it's what we used to call Dieselgate is still fresh on your minds. And yes, following scrutiny of diesel and internal combustion engines and their emissions, it was found that when starting to analyze what pollutes really the air in big cities and next to highways, it was found that actually those combustion engines are not the only ones that are polluting air. And up to 30% of all pollution comes from different sources, actually more than 30%. One of them is tires wearing out. The other one is the amount of particles coming from brakes. So there is a new legislation which is probably right now on the books and will be issued very soon, or has been issued in November, which is called Euro 7 emission standards. It calls for many things, among them the elimination of copper from brakes, because it's one of the elements we were breathing. But if we go to the next slide, we'll see that that sources such as the discs themselves are a very significant source of the pollution. Why? Discs are normally made from cast iron, and they tend to abrade, of course, the pads. And discs do not behave the same as they age and as they rust. One of the key aspects in the evolution or recent evolution of vehicles towards electric vehicles is the regeneration, electrical regeneration used instead of classical braking. When you regenerate power and you let the car regenerate instead of using your brakes, you are using it brakes less, and brakes tend to rust. Next slide, please. So there are many ways of reducing impact on particle emissions. One of them is carbon ceramics, but this is extremely expensive and used only on very, very top of the class cars, most of them German. There is a coating process we can use also on standard brake discs, which is less expensive but not fully efficient. And it was discovered that ferrite nitrocarburizing on standard cast iron brake rotors works extremely well. It has been used in North America for the last 10 years or so for different reasons. People did not want to have rusty discs in front of their dealer. Let's say dealer has them in front outside, and the customers can see that a car that has not been used for several weeks has already very rusty discs. It was not appealing commercially, and when introduced, nitrocarburizing also reduced the amount of recalls during the warranty period. Next slide, please. Thank you. So how does ferrite nitrocarburizing actually work? In essence, what you see in that small table here, the layer diagram, is that you build on top of, say, carbon steel or cast iron white layer. White layer is a quasi-ceramic layer which can take up to 10% of nitrogen volume. So 10% up to 10% can be nitrogen, the rest could be iron or alloying elements. But the interest is that it has low conductivity, which makes it interesting for corrosion resistance, and also it resists wear because it is extremely hard. Next, please. Thank you. So this is the composition, and we'll be looking more at carbon steels and cast irons. Why? Because cast irons and carbon steels do not become extremely hard. They don't produce extremely hard cases because they don't have the same amount of alloying elements as, let's say, low alloy or tool steels. But the point of interest here is that the amount of nitrogen which is diffused or which forms the white layer on the surface prevents corrosion and prevents pitting. Pitting, even if moderate, can grate discs. The disc will cause discs to grate the braking pads and emit a large quantity of particles. Next, please. Thank you. So this is the close-up. It was taken with atomic force microscope just to show you how it really looks. And you have this compound layer, which is also the compound layer, and white layer are the same. Many people prefer to use white layer. Compound comes from the fact that it has two theoretical components, which is gamma prime and epsilon. On top of this compound layer or white layer, you build a layer of oxide. It's called Fe3O4, which is basically magnetite. It is a compact oxide which prevents corrosion. It may be very thin, it may wear out relatively fast. However, it prevents discs from the onset from corrosion and helps maintain the quality of the disc during the whole lifetime. Next, please. Thank you.
Okay, thanks, Jack. Okay, this brings us to the point of process control and high quality gases. This next slide is a composition of gases that are used for heat treatment. The supply mode that Linde can provide from gas cylinders up to on-site production of each gas, as well as their purity levels to the right-hand side, as well as Linde designations of what each is. Which brings us to one of the last slides here. This is an Elingham graph, kind of showing different shows the lines of metal to metal oxides of different temperatures and oxygen partial pressures. At point below the specific line, depending on the material or alloying element, is reducing, and then at any point above the line would be oxidizing. So whether you're producing coppers, nickels, iron, titanium, or aluminum oxide. The nitrogen, an oxygen partial percentage at 0 equals roughly 10 to the 25th power of oxygen molecules per cubic meter. Nitrogen with 2 parts per million remaining in oxygen, which is 0.5, which is 5O purity from the description in the previous slide, will oxidize all metals. And to avoid oxidation of iron, for example, during carburizing, say at 880 degrees C, an oxygen partial pressure is required, which equals to about 27 million oxygen molecules per cubic meter. To avoid oxidation of chromium at 880 degrees C, an oxygen partial pressure is required, which equals to about 1 oxygen molecule per 37,202 cubic meters. To enable good and reliable heat treatment results, both the gas quality as well as an understanding of the heat treatment atmosphere are key factors. Jack.
Thank you very much, Carl. So we are running a bit over our allotted time slot. However, in conclusion, of course, it's a bit short of a time span to present all of the opportunities. However, in general, as you may have seen, the evolution of transportation and in particular of automotive and transportation, road transportation or land transportation, away from internal combustion engines towards electrification is not the end of heat treating industry. It is just a transformation. It has allowed, of course, to reduce the carbon imprint, but also has posed new challenges. One of them we have seen is the issue with brakes and the issue with pollution that we were generating, and probably most of us we were not aware of. We also are looking for new ways to manufacture parts or to heat treat them in high volume. This includes nitrocarburizing and also includes LPC or low pressure carburizing, which allow to use less gas, have a more precise treatment, and manufacture anything from gearboxes to brakes on the new generation of vehicles that we'll be seeing, or we are seeing already in large quantity on the market. Finally, we have seen the evolution in additive manufacturing. One of the key benefits of additive manufacturing is to reduce the waste of prime materials, the ability to reduce the weight of vehicles, the ability to create complex shapes which were otherwise made just by machining and spending time and money and materials, of course, which go to waste. So the evolution is still going on and will be going on. As we have seen in additive manufacturing, the techniques being used and the materials being used are evolving extremely fast. Whatever was top of technology perhaps a year or 2 years ago has been already superseded by new solutions. So I hope that you spent with us interesting hour on this presentation, and I hope that we'll be able to answer your question very shortly. Thank you.
Okay, thank you both for that excellent presentation. And before we conclude, we will be joined by Michael Graff from Linde, and we'll answer a few questions from our participants. Okay, so This is sort of a very specific question, so I'll read it slowly here. Does AMS 275910 nitriding work on pH 13.8 molybdenum? If so, is nitriding done before or after aging to H1000?
Okay,
Yeah,
it is an interesting, yes, thank you. It is a very interesting question. Yes, it does work in many respects. First of all, for pH materials as much as other materials, which let's say martensitic steels or others, requires control. So it will work because it is a chromium-rich material. And being chromium rich, it is extremely easy to oversaturate it. Therefore, you need to control nitriding potential, because if you do not, you will create excessive compressive stress and probably stress relief cracks on the surface. So that's one. Second, depending on the temperature range and the length of the process, yes, we do see hardening. So there is a precipitation process going on while nitriding. We have done this process at different temperature ranges. One of them being, let's say, low temperature processes below, in Celsius, below 430 degrees Celsius. And we have done this process at much higher temperatures. In all cases, we have seen an increase of hardness. So there is an aging process that is being done concurrently with nitriding.
Okay, thank you. And now this question came in when you were talking about all the different additive manufacturing types there. The question is about non-destructive evaluation and what kinds of technology advances there are needed for future processing with the manufacturing streams that were shown. So we're talking about what kind of NDE technology advances do you think are needed?
Michael, do you have anything to add to that?
Yeah, I think that topic, quality evaluation, testing of 3D printed parts, I think that's still very dynamic, and there are many institutes and organizations working on standards, how to define it. Similar like the AMS standards or examples that Jack showed. But there is still not the 100% guideline for that, and there will be changing, there will be something, but it's currently very dynamic.
Okay, well, thank you for that one. I got one more question here that just came in, and then we'll have to shut it down. Okay, do water atomized metal powders behave differently to gas atomized powders in a nitriding environment due to their differing mass and structures?
Michael?
Hmm.
Maybe we should split that question. I can give some answer and then maybe check if it comes to the nitriding part. I think the heat treatment step after 3D printing in general is very complex. If we distinguish between water atomized powder and gas atomized powder, there is not really good or bad. It always depends on what's the process afterwards. So if you have a classical press and sinter process, you need to have water atomized powder. It will not work with gas atomized powder, but also the other way around. If you do 3D printing, you need that very spherical powder particles. It will not work with water atomized powder. Jack,
yes, I have a very
nitriding 3D printed parts.
Yes. Okay, so I can say something about this. It really depends if those parts are near full density or full density, because that changes everything. Of course, and also additives and were there any binders? Was it debound? The process works fairly well if in some of the additions where we have seen copper being also particles being added into the mix. So it does work on certain parts, but with a word of caution, it does work, but it really depends on the part itself, because some parts are sintered, and we have worked with meme parts. We have worked with 3D printed parts, and if they are near or full density, the process will work. Again, depends on the processes following primary sintering or primary after printing sintering.
Okay, thanks guys. Unfortunately, we don't have time to answer all of the questions that we received, but in a few days, all participants will receive an email with further contact information. I encourage you to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high quality, practical information that you can use. I also encourage you to follow up with Carl and Jack for more information about the future of transport, grasping new opportunities in heat treating. Once again, I'd like to acknowledge the sponsors of today's webinar, Linde and Nitrex. Linde is living their mission of making our world more productive every day by providing high-quality solutions, technologies, and services, which are making their customers more successful and helping to sustain and protect our planet. Nitrex is the only fully integrated global player in the surface treatment industry. With a presence in more than 20 countries, their portfolio of innovative solutions and unrivaled expertise are helping customers daily to achieve greater tolerances, meet the highest standards, and become more profitable along the way. For more information, visit lindeus.com and nitrex.com. Thank you again for participating in this ASM webinar. Have a great day, everybody.
Thank you. Have a great day. Goodbye.
Bye. Thank you.